Welcome to the Power Integrations course, bringing up a flyback supply for the first time. Before beginning, please note that a number of important skills and techniques are contained in the prerequisites for this course. This course will cover the steps for safely bringing up and testing your power supply. The testing described in this course will take approximately 1 to 2 hours to complete, so be prepared to set aside an appropriate amount of time. To complete this testing, you'll need the following equipment: an isolated AC source or variac, a wattmeter, at least 4 digital multimeters, with 2 of the 4 having a high-resolution current range, an oscilloscope with a high-voltage probe, a current probe, an electronic load, and your actual load. Before attempting to bring up your design for the first time, ensure that it's constructed on a printed circuit board which follows the layout guidelines specified in the Power Integrations device datasheet. Constructing your design on a breadboard or a protoboard will introduce many parasitic elements into the circuit which may prevent proper operation. Moreover, many breadboards are not designed to carry the current levels generated by a switching power supply and may be damaged. It's also extremely difficult to control creepage and clearance distances on these platforms. Chapter 1: Terminology. We'll begin by defining 2 terms which will be referred to often during this course. The first term is regulation. When a power supply is in regulation, the controller is receiving feedback and all output voltages are stable, constant, and within specified tolerance limits. The second term is auto restart, which refers to a protection mode built into Power Integrations devices. If during operation you draw more power from your supply than it's been designed to deliver, or if at startup the output voltage does not reach regulation within a specified time, the Power Integrations device will enter auto restart protection mode. This will prevent components from being damaged by limiting the average power delivered by the supply in a fault condition. The specific auto restart on time can be found in the relevant Power Integrations device datasheet. While testing, if the power supply doesn't behave as described in this course, or if it exhibits any abnormal characteristics, please stop the procedure and refer to the PI University troubleshooting curriculum to debug the problem. Chapter 2: Design Info. Now we're ready to begin testing. As an example today, we'll be bringing up an RD115 reference design board that uses a tiny switch peak device. This supply is designed for DVD players and delivers 7.5 watts continuous, 13 watts peak. Continuous power is distributed across 4 outputs, including 3.3 volts at 500 milliamps, 5 volts at 500 milliamps, positive 12 volts at 250 milliamps, and negative 12 volts at 30 milliamps. Detailed design information and test results for this board can be found on the Power Integrations website. For the purposes of this course, we'll focus more on procedure than the actual readings obtained while bringing up this design. Chapter 3: Visual Inspection. Begin the bring-up by first visually inspecting the board to ensure that all polarized components have been inserted correctly. Although unusual, a fault, which may be caused by an incorrectly inserted component, can cause a destructive failure. Even after checking component insertion, vision protection is highly recommended when first bringing up a power supply. Chapter 4: Disable under voltage. The first step is to check for correct operation at low input voltage, so you'll need to disable the undervoltage lockout feature of the Power Integrations device if it's enabled. In most designs, this means removing the UV resistors from the board. In this design, the UV resistors are connected between the DC bus and the M pin of the top switch HX device. We'll need to remove these resistors and short the M pin to source. For other products, refer to the device datasheet to identify the correct components and method for disabling the UV function. Chapter 5: Very low voltage operation. Next, solder 2 short leads to the negative and positive terminals of the input capacitor to act as test points. To properly confirm low voltage operation, we'll need to monitor the output voltage and DC bus voltage across the input capacitor while applying a low AC input voltage. Connect a multimeter across the output terminals of the board and another across the input capacitor using the 2 test points. Both meters should be set to read DC voltage. If your design has multiple outputs, connect load resistors to any outputs other than the main regulated output. The load resistors should be sized to draw the minimum load specified for each output. This prevents these output voltages from rising outside of specification due to peak charging. If no minimum load is specified for an output, then select the resistor to draw an output current of 5 milliamps. Connect the AC input leads to the board. Be sure the AC input is correctly connected to the power supply input terminals and not the DC output. Improperly connecting the AC input can severely damage your supply. We'll also need to measure AC input power for this test. If you have a wattmeter, refer to its operator's manual for instructions on how to install it in your AC input path and configure it to measure AC voltage, current, and input power. If no wattmeter is available, connect a third multimeter in series with the AC input set to measure AC current, and a fourth across the power supply input terminals to measure AC voltage. Now, make sure the variac or AC source is set to 0 and turn it on. Slowly increase the input voltage to about 10 volts AC. You should see the AC input voltage increasing on either the wattmeter or the input multimeter. If not, confirm that your AC source is properly configured. You should also see the voltage on the DC bus increase as you apply the AC voltage. If you're using a wattmeter, the steady-state AC input power should be less than 15 milliwatts. And if you're using two multimeters instead, the steady-state AC current should read less than 10 milliamps. If you see an input power or AC current higher than this, then there is a fault on your board. Turn off the AC source and disconnect the AC input. Continuing to increase the AC voltage under these conditions may cause a destructive failure on your board. Chapter 6: Startup and Regulation. If the input power is less than 15 milliwatts, then continue to increase the voltage to 50 volts AC. Looking at the DC output voltage, if the output is in regulation, is in auto restart, or the voltage on the output meter is greater than 0.1 volts, then the chip is not damaged and is functioning normally. Continue increasing the AC input voltage to the specified minimum input voltage. If the power supply doesn't start up or reach regulation, stop testing and refer to the PI University troubleshooting curriculum to fix the problem. Chapter 7: Mosfet Drain Switching Waveforms. Now turn off the AC input, disconnect the input leads from the board, and discharge the input capacitor to a safe voltage level. Also disconnect the multimeter from the DC bulk capacitor. Next, you'll need to monitor the drain switching waveforms. Break the drain trace on your board and insert a current loop. Be sure to make this break between the drain pin of the power integrations device and any components in the clamp circuit. This will ensure that only the Mosfet current is viewed by the probe. Connect a 1000 volt or greater times 100 probe across the Mosfet to measure switching voltage. Configure your scope to view both voltage and current waveforms at an appropriate scale, and set a wide time base so that many switching cycles can be viewed in a single frame. For example, with this 132 kHz design, we set the time base to 50 microseconds per division. Chapter 8: Loading Primary Output. Now connect an electronic load to the primary output of your supply, making sure that the loading is set to 0. Connect two multimeters to the output, one across the output terminals to measure output voltage, and the other in series with the electronic load to measure output current. Use the highest resolution meter available to measure the output current. Reconnect the AC input leads to the board and make sure the variac or AC source is zeroed. Now turn on the AC input and slowly increase the voltage to the minimum specified input voltage of the design. Slowly increase the load on the power supply up to 25% of full power. The output voltage should remain within specified regulation tolerances. Continue increasing the load to full load. The output voltage should remain stable and within regulation limits. Chapter 9: Full Load Operation. If your design includes multiple outputs, turn off the AC input and remove the minimum load resistors you installed earlier. Replace each of these resistors with an electronic load until all outputs of your design are loaded. If electronic loads are not available in your setup, please refer to the introduction course for more loading options and information on how to substitute them. Connect two multimeters to monitor output voltage and current for each output, as demonstrated earlier. For this design, with a total of 4 outputs, this requires a total of 8 multimeters, with at least 4 having a high-resolution current range. This type of setup is convenient for making quick measurements. If this many meters are not available in your setup, you can use a single meter to measure all voltages by rotating it through all outputs, measuring voltages individually, one at a time. Set all loads to draw a small amount of current from each output to prevent peak charging. Again, zero the AC input, turn it on, and slowly increase the input to the minimum operating voltage for your design. Beginning with the primary output, slowly increase the loading on each output, one at a time, up to the full rated load for that output. Continue until all outputs of the power supply are providing full specified output power. Your power supply is now operating at the maximum continuous output power. All outputs should be stable and within the specified tolerance limits. If they're not, then stop testing and see the PI University troubleshooting curriculum to debug the problem. Chapter 10, Efficiency Check. While the power supply is running at maximum continuous load and load line, perform a quick efficiency measurement and compare it against the target specified by PI Expert. If you find the efficiency is lower than expected by more than 5%, then see the PI University troubleshooting curriculum to debug this issue before continuing. Chapter 11, Peak Drain Voltage, High Line. Next, decrease the time base on the scope and trigger on the rising edge of the drain voltage. Set the scope to normal trigger mode and slowly increase the trigger level until the scope triggers occasionally on the highest peak seen in the Mosfet voltage. Using scope cursors, measure the maximum voltage seen across the Mosfet at this peak. Now slowly increase the AC input voltage to maximum line voltage, pausing in 50-volt increments to increase the trigger level and measure the highest peak. If at any time the peak drain voltage measured is greater than 650 volts DC, stop increasing the input voltage to avoid exceeding the Mosfet maximum voltage rating. If you don't reach maximum line voltage before you're forced to stop, then either your clamp is improperly designed or your transformer has higher leakage inductance than expected. Resolve this issue before continuing. Chapter 12, Undervoltage Lockout. Next, reduce the load on each output to minimum load and turn off the AC input. Reconnect the UV sense circuit if it's included in your design. Also connect a multimeter across the input bulk capacitor set to measure DC voltage. Zero the AC input, turn it on, and slowly increase the voltage until the DC bus voltage reaches the lower range of the UV threshold. The power supply should start up at a voltage which is between the two limits defined by the tolerances of the power integrations device and your UV resistors. It should also start up before you reach the minimum AC input voltage for your design. In this design, we expect the power supply to start up between the range of 78 volts and 105 volts DC on the DC bus, defined by the tolerances on the resistor and device UV current threshold. Chapter 13, Peak Drain Voltage Overload. After the power supply starts up, increase the AC voltage to the minimum input voltage and load the supply to full load. On the primary output, slowly begin increasing the load while monitoring the peak drain voltage on the scope. As you begin overloading the power supply output, verify that this peak voltage never exceeds 650 volts peak. If it does, stop the test and debug your clamp circuit. Once the maximum overload power has been reached, the output will fall out of regulation. This will either trigger the power integrations device to enter auto restart or latching shutdown. The response to a loss in regulation varies by device family and circuit configuration, and can be found in the product datasheet. Auto restart is the most common. On the scope, capture the peak drain voltage seen just before the power supply enters a protection mode. If this voltage is greater than 650 volts DC, then you'll need to adjust your clamp circuit. Overloading your power supply places stress on all components and increases the dissipation in your design. This can cause components to heat up rapidly, so if you notice signs of overheating, stop the test immediately and allow time for your design to cool down. Now repeat this test at the maximum AC input voltage. Chapter 14. Peak Drain Voltage Startup. For the next test, reduce the load on the supply back to full load. If your power supply has entered latching shutdown, it may be necessary to cycle the AC input before the supply will return to normal operation. Switch off the AC source and wait until the voltage on the DC bus has dropped to about 10 volts. If a large value bulk capacitor is used in your design, this may take several minutes. The process can be accelerated using your capacitor discharge board. Now we'll examine the drain voltage and current waveforms at startup. Starting from 0, increase the input voltage to the maximum value and make sure the supply is at full load. Set the scope to normal trigger on the rising edge of the drain voltage waveform. Increase the trigger level until you find the highest level which will trigger during normal operation. Then turn off the AC and snap it back on. Continue doing this while increasing the trigger level until you capture the highest peak voltage seen during a snap-on event. If the highest voltage measured exceeds 650 volts peak, then you may need to redesign your clamp. Chapter 15. Drain Current Shape Startup. Repeat this procedure while triggering on the drain current waveform and measure the highest current seen during a snap-on event. Examine the shape of the current waveform for signs of transformer saturation. During startup, you may see one of these two current waveforms. The current waveform on the left is a normal current pulse that ramps linearly from turn on to turn off. The current pulse on the right shows signs of transformer saturation. Notice how this pulse becomes somewhat exponential towards the higher end. This is where the transformer core saturates and can no longer store energy. At this point, primary currents can increase rapidly and may damage the power integrations device or other primary side components. Plot this waveform for future reference and see the accompanying course notes for more information on this problem. During this test, it's possible to capture short pulses, like the one seen here. These pulses are normal and are caused by the lack of transformer reset at low output voltages. Chapter 16. Transformer Primary Inductance. Now turn off the AC input and connect the high voltage oscilloscope probe across the terminals of the input bulk capacitor. Then apply the minimum AC input to your supply and increase the output loading to full load. Configure the scope to view both the DC bus voltage, seen by the high voltage probe connected across the bulk capacitor, and the drain switching current. On the scope, measure the di by dt ratio of the drain current during the most linear portion of the ramp. This is typically the portion between 25 and 75% of the current limit. Also measure the average DC bus voltage seen during the same interval used to measure the change in current. Using these two pieces of information, we can calculate an approximate value of the primary inductance of the transformer using the basic relationship of inductors, V is equal to L delta I by delta T. When the Mosfet is turned on, the voltage seen across the transformer primary is approximately equal to the average DC bus voltage. The current through the inductor is the same as the drain current. Rearranging this equation, we calculate L as shown. Compare the value you calculated with the specified value in PI Expert. If it's outside the tolerances given, then contact your transformer manufacturer to resolve this problem. Chapter 17. Initial Current Spike. Check for high initial current, which occurs immediately after the Mosfet is switched on. Turn off the AC source and reconnect the high voltage oscilloscope probe across the Mosfet to measure drain switching voltage. Then apply the maximum specified AC input voltage and load your supply to full load. Configure your oscilloscope to view both the Mosfet voltage and current and trigger on the rising edge of the drain voltage. Set the time base just wide enough to monitor one complete switching cycle. Examine the turn-on edge of the drain current waveform. You may observe a spike of current. This spike is normal in switching power supplies and is caused by parasitic capacitances which quickly discharge through the Mosfet. Power Integrations devices implement a leading-edge blinking feature which disables the current limit sensor for a fixed period immediately following Mosfet turn-on. This prevents the initial current spike from triggering the current limit and prematurely terminating the current pulse. However, if the turn-on spike is larger than normal, it can still trigger the initial current limit of the device and cause it to limit power transfer to the output. Study the datasheet for your Power Integrations device to determine the minimum leading-edge blinking time for your design. Then, measure the current level you see through the Mosfet after the leading-edge blinking time. Compare this value with the initial current limit also found in the device datasheet. If the value you measure is greater than the initial current limit, then this may cause power delivery problems. Repeat this measurement at the lowest specified input voltage. If the design operates in continuous conduction mode at low line, the initial current pedestal will add to the initial current spike. Chapter 18. Bias Winding Voltage. If your design uses a bias winding, turn off the AC input and connect an oscilloscope voltage probe set to measure DC voltage across the filter capacitor for the bias winding output. If necessary, solder 2 short leads to the back of the board as test points for this measurement. Then apply the minimum AC input and remove all loading from the output of your supply. On the scope, measure and record the lowest voltage you see across the bias winding capacitor over an entire cycle. If the lowest bias winding voltage you measure is less than 8 volts, this can cause regulation problems in your design. To fix this, you'll need to add more turns to your bias winding to increase the voltage. See the course notes for guidelines on making this modification. Chapter 19. Output Diode PIV. Now we'll check the peak inverse voltage, or PIV, across the output diode. First, turn off the AC input and disconnect all scope probes from your board. Then, connect a low voltage probe across the output diode you wish to measure, connecting the ground clip to the cathode and the probe tip to the anode, as shown. We'll also insert a current probe in series with the output diode to view diode current. However, this is purely for illustration and isn't necessary for your measurement. Apply the maximum AC input voltage and load your supply to full load. Looking at the DC voltage seen on the scope, you'll notice that the voltage across the diode is close to 0 while the diode is conducting and quickly reverts to a negative voltage when it's turned off. This negative voltage is the inverse voltage. Measure the highest negative voltage seen across the diode at any point and compare this value with the PIV rating of your diode. If the value you measure is equal to or greater than the diode rating, it will fail long before the expected component lifetime. Power Integrations recommends maintaining a margin of 20% between the measured PIV and the diode rating for field reliability reasons. If your diode doesn't meet these requirements, replace it with one that has a larger PIV rating, or, alternatively, optimize your diode snubber. If your design has multiple outputs, repeat this test for all other output diodes in your design. Chapter 20. Full Load Efficiency. Next, measure and record the full load efficiency of your power supply at both the lowest and highest AC input voltage. If the full load efficiency is less than the value predicted in PI Expert by 5% or more, you'll need to address this issue. Chapter 21. Component Temperatures. Measure the temperature of key components in your design, including diodes, electrolytic capacitors, common mode chokes, the transformer core, windings, and the Power Integrations device. These measurements should be performed while the supply is at full load and has been operating at room temperature for about 20 minutes. Take temperature measurements at both minimum and maximum AC input voltage However, temperatures are usually highest at low line. Increase the temperatures you recorded to approximate for the worst case by adding the difference between the measured room temperature and the maximum ambient temperature specified. Compare these estimated temperatures with the maximum operating temperatures found in component datasheets. Be sure to factor in any derating requirements for your design when making this comparison. See the course notes for more information on component temperatures. If you see discoloration of a component or the PCB, or if a component is visibly smoking, then turn off the AC input immediately and address this problem. Chapter 22, Output Voltage Ripple. Now measure the output voltage ripple and confirm that it's within the limits specified for your design. If it isn't, or if you see significant oscillation on the output, then see the PI University troubleshooting curriculum to address this problem. Chapter 23, Startup with Final Load. Finally, turn off the AC input, remove the electronic load from the power supply output, and connect your actual load. Connect a multimeter across the output of the power supply to monitor output voltage. Set the AC source to the maximum AC voltage for your design and snap it on. Verify that the power supply is able to start up and reach regulation while powering the actual load. Repeat this test again with the AC voltage set to the minimum limit. If your power supply can't start up when the actual load is attached, you'll need to see the troubleshooting course for a supply which fails to reach regulation to debug this issue. Chapter 24, Powering Final Load. If your load has different operational modes, be sure to cycle through all of them and ensure that the power supply never enters auto restart. If it does, your actual load is drawing more power than your supply is designed to deliver. You'll need to carefully characterize your load and redesign your power supply. Refer to the course prerequisites for more information on how to do this. Thank you for attending the course Bringing Up a Flyback Supply for the first time. If you have any comments or questions, please email piuniversity@powerint.com.